Recently, I was prompted with a question from one of the well-known reviewers out there, and one of, I'd say, two that can actually do decent power meter reviews, and that is GP Llama or Shane Miller. And what he's been having trouble with is aligning the results of power meters, and the one common factor they have is that they are all on either a Shimano dura-ace FC9100, or they're all on a Shimano Ultegra R8000. And it's kind of interesting to note that that's the only cranks that they seem to be having problems on of this magnitude. So I've actually had this question posed to me multiple times over the last few months from several people in the industry, but also just general folks on saying, why are power meters on this just such a problem? Why can't I get good results? And it kind of comes down to the shape. They've evolved from this nice symmetric design with defined spider arms, even though they're integrated, they're well defined, to this weird asymmetric and, in my opinion, hideous looking crankset that has effectively only 3 spider arms, and the crank arms edge is kind of widened into where the chainring mounts. Why is this a problem, though, is actually really complicated, and I only really have a couple of tools in my tool bag of explaining this. Unfortunately, one is very high cost, and frankly, I see is kind of pointless. And that is buying the cranksets, buying some strain gauges, installing them, and running a bunch of calibration tests. When I know that this is just an extension of existing problems from the 6800 and the 9000 series, where they just took that asymmetry 2 steps further. So one of the things I found out recently is one of my favorite finite element software, if people have those, is ANSYS, and specifically ANSYS Workbench, because I love the CAD integration. I love what they've done with their design modelers and stuff like that. But they also make all their low-level tools very accessible at a high level. I'm going to have to skip over a lot of the background. So what is strain and how strain gauges work? You can find lots of videos of those online. And I'm going to kind of glaze over some of the problems with the left arm. I already talked a little bit about this, but that axial problem, you have to keep in mind that will affect future problems. So those brands out there that don't actually have a true solution and are fudging, those systems will never truly be accurate. But for the deep end dive, if you don't fully follow along, what you're looking for is things to be consistent. We need its calibration to be consistent. Regardless of the position of that crank arm, the calibration should be the same. If it is not the same, it will not be an accurate power meter. Right now, there is not high accuracy positional sensing, angle sensing. So they're not likely any companies out there using calibrations that change. And when you do that, you also have to compensate for potential differences in the chain rings, even on an integrated spider. The axial, if a company used a fudge factor over here on the left arm, they're likely going to use a fudge factor again. And they can't do that. Those cheats and hacks, they don't work. Because you need real numbers, not just 8% higher because you think it should be. And it has to be accurate. But then when we talk about coupling being when torque is applied to the left side, what happens with the right strain gauges? They are affected. And very few companies are dealing with this, but also because of how far they've taken this weird asymmetry and terrible mechanical design, that it needs to be consistent, and it's not right now. But not only that, is it needs to be consistent fore and aft, because when you're applying forward torque, it's taking the force is being held by the chainring. But when you're applying negative torque, like lifting your left leg up, it's actually going through the axle out the arm. So you need those fore-aft effects to be consistent and testable. So some problems here. How I'm choosing to solve it is by using finite element analysis. Luckily, last year or the year before, ANSYS released an updated version of the academic version of their software that I've used for over 11 or 12 years. And that allows me to actually run these simulations and show them to you without having to buy a $20,000 ANSYS license seat, which some of these companies probably should have done before they jumped into the deep end. So with that, let's go into the world of finite element analysis. So the best way to figure out all these problems that I know of is to use finite element analysis. This is where we take a crank or any other thing and we break it up into these tiny regular shapes, and we use some governing equations and figure out how they deform. And essentially they make really cool, pretty pictures, but they also can tell us things like stress and strain. So what I've done here is this whole top row is the first cut at an FC 90-100. This bottom row is where I move the strain gauges on it. The second row, a 5-arm version, and the 5-arm version where the gauges are moved. So not perfectly logical, but in how they're laid out, but it'll get the job done. So first thing we'll look at is the geometry. So this is the crank as I modeled it. It's a very simple geometry, but it gets the job done. It essentially tells me what I need to know. And one of the other great things is, yes, I've made it hollow. It's not perfect to the design, but it's close enough, and it's important that we keep certain aspects close. I've modeled strain gauges. That's these little surface bodies here. They are connected with a certain type of formulation called pure penalty. Means they have no effect on it. They just kind of read back, and we've also kind of reinforced that with these commands here. These simple commands says use this material but have no stiffness. And this, we're just using a built-in aluminum alloy. Essentially, we're not even using anything beyond the elastic property. So it's essentially the only thing that really matters is Poisson ratio of about 0.3 and 68.9 or 70 GPa for the elastic modulus. So in order to calibrate these things, what you do is you normally have an axle, but we don't need to simulate that. We just apply a force offset to the right distance. But unlike the left arm where you're held by the axle, what you're actually held by is the chain ring. And that's kind of an interesting point. So we've actually had to change kind of the setup here. So I have a cylindric support, and what that means is the radial is fixed. It can't move up and down, forward and backwards. The axial is fixed, can't move in and out along that z-axis, but the tangential, and it's in the coordinate system here of y, so it can rotate. So when we apply that torque, we need something to hold it, and we're using that first arm. So essentially you can imagine, if I can rotate it around, kind of like that you're applying a torque in this direction. So your force is in this direction because it's rotational torque, and it's being held by a chain ring, so your chain is coming off here. And we'll do it for every position. And what you'll see is, with these two strain gauges, we're going to have elastic strain in the x direction because our gauges are aligned to the x direction. And now this is scaling up the deformation. We can turn that off, but I like to leave it on. And you can see that there's some symmetry here, but there's some weirdness going on here. But when we look at our strain gauges, our top gauge is, so a microstrain is 1e -6, so I'm just going to be abbreviated. So this is about 67 microstrain in the positive, so it's stretching, and 174 in the tense, or in the compressive. Yeah, so tensile, compressive. On a good power meter, the assumption is that these are exactly identical, and we've got about 3 to 1 here. So the sign will be opposite, but the magnitude the same. It's not. So again, 67 and 173, and we change that position to up here. That's what that A is for. 53, 113, 114. So keep in mind, all a power meter like a Stages or a Pioneer or others will see is the top minus the bottom. So minus a negative is a positive. These numbers don't sum up to the same thing. So every time we go around, we're now over here, we're getting different values. Well, they sum up to different values. And that's no good. That's really, really bad. So we have no consistency for calibration. It's all dependent on the position of the chainring. Okay, well, what if we move those strain gauges? We move those strain gauges further out. So now we change that 85 to 16, 86, 87 to 19. So you can see how moving those strain gauges has made the calibration much more accurate, or for those positions. And we can keep going around and we can see it. That's great. And you'd actually be surprised to see that for a 5-arm version, gauge is kind of in the same vicinity, all the exact same setup, holding in the chainring. We get not perfectly the same numbers, but when that is no longer in the vicinity of the chainring, you know, the numbers start 187, 189. It's on the back, 188, 188. I saw that lower one. It's actually the exact same, but reversed as that top one. So we won't need to. So the other one, this one would be held here. Just flip those two values for the top and the bottom. So again, not perfect, but let's move those strain gauges again. See how we move those out? Look at what that's done. Our top bend, 209, 202. 207, 207. 208, 208, 207, 207, and then, yeah. So what we've seen is that how close these gauges are to the chain ring because of how these arms connect affect the readings. Okay, that makes some sense. You'd figure, though, that this is just a bending beam, and by the time you get back here, there'd be no impact of this because you're transiting through here. Well, that's not quite true. Apparently your bachelor's of engineering and mechanics doesn't get you that far. You're probably going into the master's territory here. So that solved one problem, but looking at that axial side, go down here, and this is axial setup. Force along the axis of the crank, held at the chainring and the cylindrical support. And when we push, they should be exactly the same. And they're not far off. It's not entirely surprising based on what's going on here. You know, the asymmetry isn't affecting things too much. Back in this region, it's significantly stiffer. This should be affecting it, and it is a little bit, but not a huge amount. But remember, we had all these bad calibrations here. All right. When we look at the same simulation with all those gauges moved, about 350 microstrain, 265. So by fixing some of the calibration issues, we've just caused massive axial problems, just massive axial problems. So you're trading off one against the other. But, I mean, it doesn't seem to matter that much what we're doing with the 5-arm version that's symmetric. You know, gauge is close, 299, 3. 299.9, 3. When they're far away, 376, 376. So the symmetry thing, like, there's no problem. So you fix one problem with the dura-ace or the Ultegra, you cause another one. So that's the first kind of calibration problems. That's the first 5 simulations we've got going on here. What are the rest of these? Well, we're going to talk about coupling. So what is coupling? Coupling is what happens is when the left is coupled to the right. So the response of the strain gauges on the right are entirely dependent on what the left is doing. And based on conventional, undergrad engineering and mechanics theory, you're like, well, if I am applying a torque through that axle, the torque is applied here, I'm holding it by the chainring, this is the path, or this is the path, or this is the path, or this is the path. And, outside of like maybe here, there's no influence. This is just a chunk of metal hanging on. But that's not actually right. So we apply a moment at that axle and hold it by the chainring, and we'll go around and we'll do the same thing, and we'll look at what the strain gauges respond to. And we have 27 microstrain, or 28 almost, and 28. So those two actually, they cancel. So that's not bad. Things are looking good for us. Down here, we've got 7 and 16. So those ones don't cancel. They leave about 9 microstrain, and that's measurable, but not huge. And, 9 and 1, again, 8 microstrain. We got, 14 almost, and 33. That leaves 15 microstrain. Oh, sorry, they're negative opposite signs. That's 45 microstrain. So this one actually causes huge impact on these now. Like it's, we're talking about the calibration for 1,000 newtons or like the whole weight of a person versus on one side. So if you split this up, like you were talking calibrations in the vicinity of, when we sum these up, 200. So when you get down to that fourth coupling, if you're in this vicinity, splitting weight, that's like 25%. That's 20 or 25% error. 25% error is ridiculous. Just hugely ridiculous. So, all right, we move those strain gauges. So, hopefully we could get those out of that zone of influence. And what do we got? Did it work? 7, 2, all right, we're down to 5. That's only like 2% error. 5, 6, 3% error. Yeah, 3% error-ish. Yeah. 4 or 5% error. So you've got some coupling stuff happening there. And that's in the improved. So we're moving the strain gauges out really, really, really far. As far as, not as far as we can yet, but, you're getting to, that's where the chainring is. If you put them out further than that, you get derailleur clearance issues. You get all sorts of other new problems. And, I'd love to say it doesn't exist on the other one, but it does. Like, this is, an issue with all these integrated spiders. It has nothing to do. So, we're actually getting worse. So, that's 41 plus 76, and we have a less stiff arm. 180, so, but 41, that's still like 25, 30% potential error. Okay, so obviously, if you're too close, your coupling effect is wonky, but it's also inconsistent around. We also saw that like it changes depending on which positioning you're at. Did it get any better here when we moved those gauges? Not perfectly. So that first coupling is still rather large. So, we're adding 4 to 30, and we're talking a calibration of 400. So, we're still talking 10%. We're still down, like this is down in the 10% range. And when we move, it'll be, yeah, now we're getting into the minuscule, the nothing percent range. Again, the nothing, e to sevens, e to the sevens, e to the six. So yeah, it's getting back, and then fifth coupling, yeah, back into the same. So whenever we're close here, so when you're applying, so this is at the bottom of your stroke. So this crank is pointed up like this. So it's that forward torque. And, that's kind of the dead zone. So you don't see that huge, massive 40% error there. But even a little bit of forward torque is going to cause some massive error in that zone to see if I can't rotate it the way I want. But that's all well and good, except for there is another thing. This is what happens when you're applying left forward torque, but when you're applying left backwards torque, you're not held by the chain rings, you're held by the crank arm. So then it looks like this. So it just looks like kind of a standard left arm calibration. So now what we have to look at is how different is this calibration to the chainring calibrations. And for this one where it's moved, 208, what we're averaging here too. So we're looking at 414 total. And we've got 418. So that's pretty good. But move on back to where the gauges are close. A decent calibration is 187, 189. So, math in head is hard. 390, 380, yeah, 395, 395-ish. Yeah, they're not bad. The calibrations on the 5-arm are close. Great. What about that FC 9100? Start with the worst case scenario. I have to look at one of those back arms, so we're looking at through the simulation. 114 and 53, so 167. 53, 108, 53. Yeah, that's actually really close. All right, so the negative coupling kind of matches the regular calibration. I mean, the positive didn't, but, and when we move to this one, let's see what we get. Well, our calibration's changed to 220 plus 86, so 306. A bit higher, so there is some difference there, but it's different than the effect from the negative calibration. Like these are just on their own, so they're not symmetric. So this is what really leads to all the problems. So I think at this point it's time to show you a summary. I summarized a lot of this data so that I wouldn't have to go through it while I was going through the FEA. So with the calibration values, when we moved it really far out, those gauges really far out, it reduced a 48% error, which was a bit unrealistic. It was obviously too close, but I mean, could actually happen on these newer cranks, down to 2.3%. And that's still kind of high, but what's happening is somewhere in here, somewhere between these two values, that's exactly where real 9000 or 9100 series cranks are existing in terms of their calibration error. So they don't read correctly instantaneously at all. When we look at the 5-arm, yeah, when it's really close to those spider arms, 24% error in their calibration, but when we move it a little bit further out, it's down to 1.2. And that's much better. Like realistically, you notice that, that theoretical error turns into a much, much smaller number. But when we talk about the coupling again, so this is the percentage coupling, and sorry, the scale is it's not actually in percentage, but so 0.1 is actually 10%. You're actually seeing some huge numbers here. So the forward torque in the blue, starting like pretty flat around 5%, but between 0 and -20, and near that -20, that gets near that forward torque dead zones in the vertical. But yeah, the negative torque too is actually negative. So no matter what you do, it causes this thing to read down, and that seems to be the big error. But we also move those gauges. So this was the worst case kind of scenario. We move those gauges, and it damped a lot of that out. The moving that, like the negative torque, it now causes it to read high, and the positive torque causes it to read low. And yeah, but they're weird shapes. They're highly inconsistent. When we compare this to a 5-arm version, we get this good symmetry. It's not perfectly, but for the vast majority, it's hovering around kind of this plus or minus zone, and it means forward and negative torque almost canceling. You're down into a few percent. So like near the dead zones, the numbers go really high, but you're not doing much there. But then when we move those gauges out, just like we did on that 9100, it dropped right off. So we're down, worst case scenario is 0.08, so 8% error. But that's for the curve that we're not in. We're normally on that negative curve in those zones, sub 2%. So like you can actually turn an older 5-arm symmetric hollow forge like a SRAM Rival OCT into a decent power meter, but that 9100 and the 8000 series cranks, they're just a mess. If you sat through all of that, congrats, thanks, I really appreciate it, and hopefully it was informative and useful to you. If you just skipped ahead, doesn't matter. We're going to talk about those results, and hopefully you didn't skip too far through the results, but we have to look at this as a chain of events. So we have to start with the non-drive side. And as I've mentioned many times, there are two methods of dealing with this. If you have a single bending arrangement, like many of the products out there, especially all of the Chinese-based clones, well, then you have a constant calibration factor, but you have a fudge factor. And essentially that fudge factor is to take out, if you put in a lot of axial force, it will read low. And so they just dial those up a bit. You can actually trick yourself into doing this by actually, for a lot of these, increasing the length of your axles. Just calibrate further out. Even though the platform is 55 from the edge, you calibrate at 60 or 70, and you delude yourself into thinking you solved the problem when you just fudged up your calibration factors. The real way to do it is to compensate it. So when there is an axial force, you compensate it out, and you have to kind of hope they're not perfectly symmetric, and that leads us to still about 1.5% error. But that fudge factor, that's like, I've seen on good cranks as low as 2%, on really bad cranks, 8, 9, 10%, and then you fudge it up like 4 or 5%, you're getting plus or minus 4, plus or minus 5. Worst case, maybe plus or minus 6 on some of these new ones that I haven't seen. But on the drive side, as you saw, the calibration as we go around is not consistent. So right off the bat, everyone's using a constant calibration factor for it, but depending on where you put those strain gauges, could be really high as 25%, or really low, 2.5%, but still outside of those claimed errors. The ideal, which I don't see anyone implementing yet, is the calibration is completely dependent on the angle and the instantaneous force. I don't know of anyone doing this. I don't know anyone has that sophistication yet. However, as we drop this down, especially on those dura-ace and Ultegra designs, axial went through the roof, way worse than over here. So fudging, benefit of the doubt, we'll say it's the worst left arm I've ever seen. So we'll use that as the gauge, and we'll just port it over and say plus or minus 6%. Not great. We compensate, maybe back down to a 1.5. But a lot of the drive sides don't have axial compensation. So coupling. coupling is dependent on that left data. And it's dependent on not only the left data, but instantaneous forward torque or reverse torque. So if you do nothing, seeing 10 to 30%, maybe if you did a constant, if you moved it and positioned things well, you know, you might be able to get in that plus or minus 5%, but it's 5% assuming this is perfect. But we already know the guys are fudging those numbers out there, so they're adding 6% on that. This 5 then turns into a 6 or a 7%. The holy grail, again, positional with forward and aft compensation. And it makes it complicated to do this because there's a lot more data having to be calculated constantly. Potentially not even linear. And I mean, like at that 0 point, you'll have one curve and then you'll have another curve. So when you take all of this into account, you consider that the best might be doing this, might be doing this, and might be doing this, you're still left with way more percent than anyone's claiming. Now, if you're a nominal rider as how they tested it and how their cals were created, you might be plus or minus a few percent. But if you're on those edges, if you are that rider that pedals a little weird that they didn't expect, and their compensation method doesn't work for that, and a compensation method is just a cheat in some cases. The fudge factors are the real cheat, but sometimes there's limits to these compensation from other gauges. And if they don't have those gauges, you can't just software update magic to fix this. And that's where we're probably at right now. So if I was out in the marketplace right now for a power meter, I would not touch anything that's put on a Shimano-based crank right now, especially the R8000 and the R9100. They have too many chains of error. This all existed on the 6800 and the 9000, but it was much, much easier to fix. These numbers were much smaller. So with that, hopefully you didn't buy one. Hopefully if you're in the market, you're going to look at other alternatives. And I saved you from some headaches with some bad data. So with that, thanks for watching, and hopefully you all learned a little bit more about the coolness of finite element analysis.